So we all know the AI revolution is here, right? But what's actually powering it? Well, it turns out it's a completely new kind of infrastructure, and it's facing engineering challenges on a scale we've literally never seen before. Today, we're going to go inside the machine and see exactly how these massive AI data centers are being designed and operated.
Let's just start with a number that frames this entire problem: 1 gigawatt. And to be perfectly clear, that is not for an entire company's cloud operations. Nope. That is the power required for one single AI data center campus.
So, what does 1 gigawatt even feel like? To put it in perspective, that's roughly the power needed for an entire major city, like San Jose, California. Yeah, we are literally building city-scale power infrastructure just for computation. It's kind of mind-blowing.
And this forces us into a whole new way of thinking. You see, we're not just building data centers anymore. We're actually constructing entire cities dedicated to artificial intelligence. But these aren't your typical cities, and that's where the real engineering challenges begin. Think about it for a second. A normal city has millions of people doing millions of different things, which makes power usage, somewhat predictable. But an AI city? It has hundreds of thousands of GPUs, those specialized chips that power AI, all starting and stopping the exact same massive task in perfect synchronized unison. This creates a power profile unlike anything our grids have ever had to manage. So what's the first huge problem this creates? Well, that synchronized workload leads to what engineers call wild power swings. And trust me, it's a nightmare scenario for a traditional power grid that was never ever designed to handle it. At the heart of all this is a problem called load oscillation. And we're not talking about a gentle rise and fall of power. No, this is a violent, instantaneous swing as that entire digital city of processors changes tasks at the exact same moment. And this breaks down exactly why that happens. So, an AI model is training, right? It's using 100% power. Then, the entire cluster pauses to checkpoint, which is just a fancy way of saying it's saving its progress. Instantly, power use can plummet to just 30%. A few moments later, bam, it shoots right back up to 100%. A traditional power grid just can't react that fast. No way. And if that wasn't already enough to deal with, it actually gets even more extreme. On top of those oscillations, you've got something called electrical design power, or EDP. The best way to think of it is like the turbo mode on your computer's processor, where it briefly draws a huge amount of extra power for a burst of performance. Now, just imagine that happening at city scale. With EDP, hundreds of thousands of GPUs can all decide to turbo at the exact same instant. What does that mean? It means our 1 gigawatt campus could, for a few milliseconds, suddenly demand 1.5 gigawatts. It's a massive, instantaneous power spike that the grid simply cannot provide. So what's the big takeaway here? You can't just plug these massive facilities into the grid and hope for the best. The solution requires building incredibly sophisticated systems inside the data center to tame this electrical beast before its chaos ever reaches the public utility. And the solution is this fascinating three-layer approach. It combines intelligent software, direct hardware controls on the GPUs themselves, and, this is the crucial part, a huge buffer of on-site energy storage to absorb all those shocks. Now, you can manage these swings in basically two ways. The brute force method is to just burn power, run dummy calculations to keep the load constant. But the much, much smarter approach is to use on-site batteries. During a power lull, you charge them up. During a spike, you discharge them. It smooths everything out and is just vastly more energy efficient. Okay, so let's zoom out for a minute. We've talked about managing the data center's internal chaos. But what happens when the chaos comes from the public grid itself? This brings us to what's called the Grid Citizen Challenge, which is really all about being a good neighbor to the power grid. The key concept here is something called low voltage ride-through, or LVRT. In simple terms, it means if there's a problem on the public grid, like a brief voltage dip, regulators now require these massive data centers to stay connected and actually help stabilize things, instead of just disconnecting to protect themselves. And the reason why is absolutely critical. Just look at the alternative. A voltage dip happens. Let's say 5 gigawatt-scale data centers in one region all disconnect at once to protect their hardware. Well, that sudden massive drop in demand sends a shockwave through the grid, potentially tripping power plants offline and causing a regional blackout. It's an incredibly dangerous positive feedback loop. This means the entire philosophy of the uninterruptible power supply, or UPS, has been completely flipped on its head. A traditional UPS was like a fortress built to protect the data center from a chaotic grid. But today's enhanced UPS, it's designed to protect the grid from the chaos inside the data center. A total reverse. All right, so we've tamed the electrical beast. But all of that power has to go somewhere, and it all becomes heat. A staggering amount of heat. So the next massive challenge is solving the thermal problem. How in the world do you cool a digital sun that's packed inside a building? And as you can see here, traditional air cooling just can't cut it anymore, not even close. A standard air-conditioned server rack maxes out at around 30 kilowatts of heat. But today's AI racks, they're already generating over 100 kilowatts, and future designs are aiming for 500 kilowatts or even more. At that kind of density, the only answer is liquid. The technology that makes all of this possible is called direct-to-chip liquid cooling. Instead of trying to cool the air in an entire giant room, you bring the cooling directly to the heat source. A metal cold plate sits right on top of the GPU, and a specialized liquid flows through it, pulling heat away with just incredible efficiency. This slide just brilliantly illustrates the elegant two-loop system they use. You've got this highly purified inner loop of liquid that actually touches the hot chips. Then a heat exchanger transfers that heat to a second, outer loop of regular facility water. Finally, that warm water gets pumped outside, where these huge dry coolers safely release the heat into the atmosphere. It's a really clever journey. Now, what's really crucial here is the sustainability of this design. Both of those liquid loops are 100% closed systems, and because the external units are dry coolers, they don't use evaporation. The incredible result? A system that can cool a digital sun while having a net water consumption of 0. So let's just quickly recap the key ideas here. First, we're building AI infrastructure that needs the power of an entire city. Second, this demands revolutionary new power management to handle these wild oscillations and be a responsible grid citizen. And finally, it all relies on this advanced, water-free liquid cooling to manage the incredible amounts of heat. And all of this leaves us with a final, big question. We've just seen how our most basic physical infrastructure, power and cooling, had to be completely re-engineered from first principles just to handle AI. So as this technology weaves itself deeper and deeper into our world, what other fundamental systems, from our economy to our education, are going to need to be rebuilt from the ground up?